Okay, hello everyone. Today's topic is going to be more asymptotics. We're going to talk about factorials and binomial coefficients. Before we quite get into that, I want to recap something that I did hurriedly last time. So these factorials and binomial coefficients come up a lot in probability, which is something that we'll be getting to soon in this course. So I better recap this probability example we did last time. In particular, a calculation we do here will come up later in the course, later in the lecture as well. So let me do it a little bit more carefully. So last time we were talking about this thing that is sometimes called the birthday paradox. Not really a paradox, but it refers to the fact that you need surprisingly few people in a room before you're likely to have two at the same birthday. So a slightly stater way to phrase it is in terms of balls and bins. So let's imagine this setup. You have m bins and you have n balls, and each ball is thrown randomly into a bin. There are 365 bins and n people, then it's like you imagine each one has a random birthday. And what we're going to look at is the probability that every ball goes into a different bin. So there's no bin with more than one ball in it. So we'll write Pnm for the probability that there are no collisions, no bins with more than one ball. And it's not hard to write down the exact probability for this. The probability that the first ball is by itself is 1. Condition on that, the probability that the next ball is by itself is 1 minus 1 over m. Condition on that, the probability that the next ball is in a bin by itself is 1 minus 2 over m, and so forth, as we mentioned last time. And I guess this is right for all values of n, but you see this becomes 0 once n is at least m, and that makes sense because once you have more balls than bins, then you're definitely going to have a collision. Okay, so we'll assume that n is at most m. So this is an exact formula, but it's kind of not pleasant because it's a giant product and we don't really understand its asymptotics. Now, the more principled thing to do when you have a giant product is to take the logarithm to convert it into a giant sum and then deal with a giant sum, because that's usually easier. But we're just going to leave it as a giant product so that we can illustrate this approximation I talked about last time, which is that e to the x is approximately 1 plus x for small x. And in fact, let's do something that's a little bit more precise. We have expressions that look like 1 plus a small negative number here. So let's look at negative x. So here's a little plot here. This is a plot of e to the minus x. I guess this is 1, this is 0, this is x. And here's a plot of the thing that it should be close to, 1 minus x. I guess that looks like this. That's 1. This is 1 minus x. Okay, so one thing you can see is that e to the minus x is greater than or equal to 1 minus x for all x greater than or equal to 0. Okay, so that's not hard to prove, and it's like a factual version of this, one side of this approximate equality. So we can use that directly here. Let's see. To get that, I have it the wrong way in my notes. E to the minus x is bigger than 1 minus x. That looks pretty good. So this should be bigger than so this should be less than, good. P and m should be less than or equal to e to the minus 0, e to the minus 1 over m, e to the minus 2 over m, to e to the minus n minus 1 over m. Let me also reintroduce this notation. X of t means e to the t. Okay, so this is x of minus 1 over m. We'll factor that out like I did last time. 0 plus 1 plus 2 plus dot 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 plus n minus 1. Okay, and we know how to add up the first n minus 1 numbers. And this gives us x minus n minus 1 over 2 m. Okay, so I did that last time, and then I ran out of time and said, well, this is approximately right. It would even be nicer looking if we wrote it as x of minus n squared over 2m. You have to be a little bit careful to do that. But let's be a little bit more careful now. So this actually only gives us an upper bound, even though this turns out to be extremely accurate, we would like to have a lower bound as well. So how can we get a lower bound? Well, I'll just leave this as an exercise for you, that in the other direction, 1 minus x is at least e to the minus x minus, well, let me put epsilon here to emphasize I'm thinking of it as a small number, c epsilon squared for all epsilon between 0 and 1, and some constant c. Okay, so basically the next term here is big O of epsilon squared. Yep?
Does the c depend on epsilon?
No, sorry. So this is for a universal c. I was too lazy to write it, but there exists a universal c, probably like 1 or maybe 2 or something, maybe even smaller than 1, such that this holds uniformly for all epsilon. Thanks. Good. Okay, so this is like a bit annoying and grungy, but you know, eventually you have to do things correctly, so here we are. So we can use this to get a lower bound for p. Okay. And, well, these terms are the terms that we have here, so they'll give us the exact same thing as before. So we'll get the same thing as our upper bound. But we'll get these extra quadratic terms that are a bit annoying multiplied together. So we'll get times exp. We factor out the minus c. And we'll get like 1 squared over m squared plus 2 squared over m squared plus dot 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 plus n minus 1 squared over m squared. Okay, sorry the c's also look like parentheses, but there we go. Okay, and so this m squared can come out here. So let me just write that this factor here is like exp. So we have minus some constant c over m squared. And now we have the sum of the first n squares. So what is that big theta of? Yeah, n cubed. I mean, it's, I don't know, n cubed over 6 or something, but we're just going to remember that it's n cubed. Okay, so let's just put this c inside this theta. And we can therefore conclude that this is, well, let me just leave it like this. Okay, and now, let's actually make it look more intelligible by using this one again. I mean, we have e to the minus some expression that we hope is small. And it'll be more pleasant if we write it like this. So therefore, I will say that this piece is at least 1 minus big O of n cubed over m squared. Okay? Yeah? This one? I used this lower bound on each of these factors in the same way that here I used this upper bound on y minus x for each of the factors. And you see that the upper bound I'm using is like e to the minus x. And the lower bound I'm using here is like e to the minus x times e to the minus cx squared. So all the e to the minus x stuff will give me exactly the same thing that it gave me here. That's this factor. And here I collected up the e to the minus cx squared stuff, which is kind of like the gap or the error between like my upper bound and what my lower bound is. Okay, so let me summarize this here. I'll write it a bit more clearly. Okay, so what we concluded is that P and M is at least the same thing as our upper bound, namely e to the minus n minus 1 over 2m times this annoying factor. Well, there's got to be some error somewhere. 1 minus big O of n cubed over n squared. Which, by the way, actually, this could be a terrible bound compared to this one. This might even be negative if n cubed is bigger than m squared. So if n cubed is bigger than m squared, then maybe this was a dumb move. But I'm mostly going to be worried about the case when n is pretty small compared to m. So let me just leave it at that. OK, let me just write that. This is small. This thing is small. If and only if n is a lot less than m to the 2/3. OK, so actually, we could be done here. We could just say, well, the answer is basically this, up to a factor that is close to 1. I mean, it's tending to 1, at least as long as n is not too big compared to m. But also, just for a little bit of exercise, I want to go a little bit further. In the same way I was talking about last time, it's like kind of slightly annoying that you have n times n minus 1 here. Like, it would be really cool if you just had n squared, because then you could invert it and see that this equals a half when m is root 2 ln 2 times root n or something, like we did last time. So just for the sake of exercise, let's worry about that. So let's say I wanted to compare this factor with the simpler thing that just had n squared up here. Well, the way you always do that is to factor out the piece that you wish you had and see what junk is remaining. So e to the minus n minus 1 over 2m, I guess it equals e to the minus n squared over 2m. That's the simple thing I wish I had. And then the leftover is plus 1 over 2m. OK? We can use the rules of exponents to say this is the thing we care about, e to the minus n squared over 2m times exp 1 over 2m. And let's use our favorite approximation about this thing, too, because 1 over 2m is a small number. So this thing is at least 1, and it's at most 1 plus order 1 over m.
Should it be n over 2m?
That looks better. Yeah, good. N over 2m. Thank you. Good. And this fact is true because, we're using here that n is at most m, so this is a number that's at most 1. Good. So therefore, if we really want, let me conclude it here. We can put these things together and say that p n m equals this enjoyable term, e to the minus n squared over 2m, times two factors that are close to 1. This kind of slop and this slop. So I'll put in this slop first. 1 plus order n over m, and 1 minus order n cubed over m squared. Now this actually, a mildly subtle thing has happened here. We have two error terms, and it's not even clear which one is dominating. In fact, neither of them always dominate. Sometimes this is bigger than this, and sometimes this is bigger than this. Depends on how an m and an m relate. So let's in fact think about which term dominates here. In terms of the error crossover, it occurs, when they're equal. So when we have n over m, up to constants, n over m equals n cubed over m squared. So let's solve that. N squared equals m, so n equals root m. OK. So what we can say, if we call this, piece error, guess we could say that the error is 1 plus or minus order n cubed over m squared. This one's bigger when n is small. N is less than root m. And order n over m if n is bigger. And finally, remember last time we were interested in, like, how big should n be as a function of m, such that this probability is right in the middle, like around a half. Like it's neither really likely nor really unlikely to have collisions. It's like 50-50. Let me squeeze it onto this board. So we saw last time that x minus n squared over 2m equals a half. Well, we can solve this easily enough if and only if n is like root 2 log 2 times root m. Okay, or even just forgetting about that exactly, root m. Okay, so somehow like the most interesting phase transition occurs when the number of balls gets to be square root the number of bins. That's where it kind of goes from likely to unlikely for there to be no collisions. And actually, it's kind of interesting. That's where like the error terms become about the same. They're both like order 1 over root m. Okay, so for example, we could therefore conclude, and we might actually even like to conclude, since this is not literally an integer, we can conclude that we can check that for n equals this quantity, root 2 log 2 root m, we have that p and m equals a half plus or minus order 1 over root m. Actually, I omitted one little thing here, but I don't want to dwell on it too long. On one hand, this order 1 over root m comes from both these error terms when n is around root m. And, oh, actually, this is exactly true. So I didn't omit anything for this. But even if you put in plus or minus 1 or plus or minus order 1 because you want to imagine n is an integer, if you plug that into here, you'll still also only get an error that's like this. Okay, so that was the last thing I want to say about that. Any questions? So partly I went into some detail just to show you like one more example of like going into detail about, I don't know, doing the last details of some of these annoying approximations.